So by Erder-Stone, oops, it says that the extremal number of h is like, so it's chi of h minus 2. So I'm going to write this in a slightly different way, but it's the same thing. So it's this times n choose 2 plus little o of n squared. So remember, we know what little o means. It's like, yeah, for it, this thing grows slower than n squared. And so if the chromatic number of G is like 3, then, or 4 or 5 or whatever, I mean, this gives me a nice bound, right? So let's say chi is 3, this gives me 1/2 n choose 2 plus little o of n squared. So it's kind of like n squared over 4, roughly. What if the chromatic number is 2? So what does it tell me? So for example, if I take like, yeah, complete bipartite graph or an even cycle or something of chromatic number 2. Sorry, was there an answer coming through? Exactly. Yeah, so it tells us it's little of n squared, but yeah, but in some sense that now we sort of don't really know what the growth rate is, because we just know it grows slower than n squared. Like you can say, I mean, does it grow like, you know, n to the 3/2? Does it grow like n squared over log n? Is it linear? You know, there's kind of, now we, you know, before we kind of knew up to a constant, or even not even just, like we even knew, so for chromatic number 3 or greater, we know the growth rate like kind of perfectly up to a small order term. We even know the constant factor that comes in front of the, you know, the n squared. But here now we have a lot of different options and we don't really know how fast does this thing grow. Like at least Erder-Stone doesn't tell us the answer. So the question of like, what is the extremal number of a bipartite graph is actually a very interesting and very kind of deep question. And in most cases, it's just not known. Like people just do not know the asymptotic growth rate of these extremal numbers for bipartite graphs. So bipartite graphs are hard for this question. So what we're going to look at today and tomorrow is, and maybe, I can't remember if it's the day after that as well, but probably just today and tomorrow, or sorry, Monday. But yeah, today and tomorrow we're going to look at some specific examples of bipartite graphs and, you know, bounding these extremal numbers. Okay, so is it clear what's going on? Okay, so let's look at, so today we're going to look at, I think, you know, one of the simplest type of bipartite graph you could have, which is a complete bipartite graph. So a kind of standard definition for S and T at least 1, KST is the complete bipartite graph where the, you know, parts have size S and T. I guess we've been looking at complete bipartite graphs a lot because they were the examples for Mantel's theorem. But yeah, this is, I guess, just notation, KST. So what we're going to prove in the rest of this lecture is the Kővári-Turán theorem, which says that, well, it gives an upper bound on the extremal number of a complete bipartite graph. So the extremal number is at most, well, you know, maybe, so there's a little bit of a kind of error term here of 1 plus little o1 times 1/2 t minus 1 to the 1 over s times n to the 2 minus 1 over s. Okay, so there's these constant factors and stuff which just depend on t. They don't depend on n, or sorry, t and s, but not n. The really kind of important part is this last factor, which is the 2 to the, or sorry, n to the 2 minus 1 over s, which kind of tells you, it gives you an upper bound on like how fast this grows as n goes to infinity. So is it clear what this thing is saying? Yeah, basically, so the 1 plus little o1, all I really mean is that it's like at most 1 plus epsilon here, provided that n is bigger than some function of epsilon. But basically, I can't remember exactly how, so we'll see, hopefully we'll see how this kind of manifests in the proof, but this is just like a, I mean, it's kind of like, so in Erder-Stone we had like chi minus 2 over chi minus 1, n choose 2 plus little o n squared, which I could have written as like 1 plus little o 1 times, it's just a different way of writing the same thing. So I guess what I'm saying is that the upper bound is at most like all of this stuff plus some function of n that grows slower than this, if that makes any sense. So this is the main thing, and then there's some other stuff that grows slower. Okay, so a couple of comments. So the second comment I've already kind of addressed, that Earthstone only gives you an upper bound of little o n squared, and this is something better, right? This is an exponent which is less than 2, n to an exponent less than 2. Another thing is, like, every bipartite graph is contained in a complete bipartite graph. So this actually gives you an upper bound on the extremal number of any bipartite graph, right? Because if I have a graph G that forbids copies of H, right? So this graph G doesn't have any copies of H, then it also can't contain like a complete bipartite graph of whatever are the right sizes, right? Like if so if it doesn't contain H, and H has like S vertices in one bipartition or part of the bipartition and T in the other, then it also can't contain a KST because a KST contains H. So forbidding H will also forbid KSTs, and this gives so you get an upper bound on this thing for every bipartite graph H. Okay, so let's try to prove this. So suppose that G is KST free, so it has no KST subgraph, and I want to bound the number of edges in G. Okay, yeah. So the second comment, if you've been writing things down, it's already kind of covered by the other stuff I've said. Actually. Yeah, no worries. Okay, so I want to upper bound the number of edges in this graph, which doesn't have a KST. Okay, so let's count. So we're going to do some sort of double counting stuff. So let's count pairs VA, where V is a vertex of G, and A is a subset of the neighborhood of V, such that the size of A is S. And I'm going to call script or curly P. I'm going to let that be the set of all such pairs, VA. Okay. So a question, I guess, for the audience, like if I have a vertex V, how many sets A are there like that we're counting here? So I guess how many subsets of the neighborhood have size S, I guess is what I'm asking. And by the way, this is the same as counting copies of like K1S, right? It's just a vertex and a set of S vertices that are adjacent to that vertex. So yeah, so size of the neighborhood, or in other words, the degree of V, choose S. Okay. Yeah, that's exactly what I was going for. But now what if we count this sort of from the other perspective? Like if I take a set A, how many vertices V could there be which are all adjacent to A? So A is a set of size S. And remember, G is KST free. So I can't count the number exactly. Like if I take a set of size S, there might be 0 vertices that join, S. There might be 1 or 2 or whatever. I can't count it exactly like how I counted this. But what can we say about that? Right. If I take, so take a set of size S, how many V can there be such that VA is in P, I guess? And I mean, the point is this graph doesn't have any KST, right? So if I've got a specific set of S vertices here, every time I find a vertex V where VA is one of these pairs I'm counting, it looks like this, right? But if I found T of them, I'd have a problem because that makes a KST. Is that clear? So there's certainly, for every subset, there's at most T minus 1 vertices V such that VA is in P. Okay, so this tells me that the size of P is at most T minus 1 times the number of sets of size S. Oh yeah, so wait, which way did I go here? Anyway, it doesn't matter. I think I asked these questions kind of backwards from what I planned. But anyway, so the size of P is equal to this, right? By, what we said on the previous slide. but it's at most this, because every set can only have t minus 1 vertices that kind of form a k1s with it. Okay. Yeah, this is kind of ugly, but so the point is that like the sum of the degrees choose S is equal to the number of these pairs, which is at most t minus 1 and choose S. Okay, and I'm going to be a little bit sloppy because you remember there's this like 1 plus little o 1 thing, so I don't really care about, I don't know, small order terms and stuff like that. So I'm going to kind of throw a little bit away here. So I'm going to just upper bound this by t minus 1 n to the s over s factorial, which is true, right? N choose s is like n times n minus 1, n minus 2, blah, 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 like down to n minus s plus 1. And all of those are at most n. So I can just kind of, and then divided by s factorial. And this one is at least like, I can say, I sum over all the vertices. I could take like degree of v minus s to the s over s factorial. Okay, I could even write, I think, minus s plus 1 here. Are these bounds clear? Oop. Yeah, exactly. I'm looking at I'm kind of canceling a few things in the n choose k formula. I'm looking at the numerator, and the denominator is just s factorial, and I'm just, being a bit wasteful. Okay, so yeah, this is basically what I had on the previous slide, up above. So the s factorials cancel, right? So I'm just looking at this kind of left thing and this right thing. Like these are all I care about. So the s factorials cancel, and so it becomes this, right? And here's the thing, like, so here I've got, on the right-hand side, I've got a sum of, essentially I've got the sum of the degrees, although it's not quite the sum of the degrees because there's this minus s. Sorry, not the sum of the degrees, but the sum of the degrees to the sth power. I'm trying to say sth, sth power. I think I had this problem last time. But yeah, so that's not that useful for us because that's not going to tell us much about the number of edges, the sth power of the degrees. But if I knew the sum of the degrees, that is 2 times the number of edges, right? We know this like handshaking thing, right? So I would like to, instead of having this on the right-hand side, I'd like to have something involving the sum of the degrees. So because I want to bound the number of edges. And this is not the number of edges. And it turns out like the right thing to do is apply one of these convexity things that we learned about a few weeks ago. So if you take, so s, remember s is at least 1. And if you look at this thing in the, up here on the back of my video, and you apply this with p equals s, okay, then, and you divide both sides by the n to the p minus 1 thing, then you get the right inequality. So this is, right, so this is at least the sum of, so instead of adding up d of v minus s to the s, you add all of these things up and then take the whole thing to the power s, and it's divided by n to the s minus 1. Okay, so this is just by this convexity thing. Oh yeah, it's also here on the slide. And now this does look like the number of edges, right? Or 2 times the number of edges or whatever, right? If I add up, this is kind of like the sum of the degrees, right? Except minus s times the number of vertices. And the sum of the degrees is just twice the number of edges. So minus, again, Sn, or s times n. So then we're in pretty good shape. But so is it clear how I've gotten this far? So all we're going to do now is plug in this 2e minus Sn, s times n, into this thingy, right? So that's what we've done here. And now we just solve this for the number of edges. So multiply both sides by n to the s minus 1, and then take the sth root of both sides, and then add Sn. So basically solve for e of g. Oh, and then divide by 2. Yeah, that is interesting. So So actually, maybe I'll address that in a couple of minutes. But that's a very good question about how good is this bound. It turns out it sometimes is pretty good. But anyway, so this is, and then now to address this question from before about this like little o1 thing, this, like the little o1 comes from this, that there's, this linear term which is growing slower than this. Although if I think about it, I may have to say that. So I think in the statement of the theorem, I wrote that s and t are at least 1. I think I probably sort of need to say s is at least 2 in order for this to really be a little o1 term. Because if s is 1, here I get an n, right? But yeah, so this is just some extra thing that grows slower than n to the 2 minus 1 over s. Okay, any questions about that? Okay. Okay, well, maybe let's not... Yes, let's address that question from before. So yeah, so a very natural question is like, how good was this bound? We were a little bit wasteful because we upper bounded n choose s by like n to the s over s factorial and stuff like that. But I mean, that wasn't a big issue. You can make things a bit tighter by keeping track of those things, but let's not worry about that. But yeah, a question then is like, is this bound tight, right? Because if I can find a graph which doesn't have KST, which has, almost this number of edges, then that'll be a good kind of verification that this proof we weren't very wasteful, right? If we can find a graph that basically matches this upper bound, then we'd be quite happy. So the bound that we proved is like something like this, right? It's like an n to the 2 minus 1 over s, where there's a constant factor here which depends on t and s. But if we just kind of care about roughly how things work, so this does turn out to be tight in a few cases. So for the case s equals 2, it is tight. In fact, the constant factor that you get, which is like, so there was this 1/2 t minus 1 to the 1 over s constant factor. If you plug s equals 2, you get like, you get roughly square root t. It's actually square root of t minus 1, but let's not worry about that. So in fact, there's a construction which basically matches this bound. Okay, and the construction is built in some kind of algebraic and kind of geometric way. So it's kind of, a little bit complicated. So it's a little bit beyond what we want to do in this course, I think. Also in the case 3, it's tight. But for a long time, like, these were the only examples where anyone knew that you could actually match this bound. Until like the 1990s, when some people proved a really kind of bizarre statement that as long as t is way bigger than s, so t is greater than s minus 1 factorial, so t being like this, like KST, so you've got t is the big side of the bipartite graph and s is the small side. If t is way bigger than s, then again, there's a construction which matches the upper bound up to a constant factor, which is bizarre, completely bizarre. But this kind of tells you that at least in a kind of wide variety of cases, at least kind of infinitely many cases, we have that this bound couldn't have been very wasteful because it's actually tight. Meaning, there's a graph that achieves that number of edges. Is it clear what I'm trying to say here? Okay. Yeah, and like I said, the examples, so, I mean, the examples are much different than what we were dealing with in the Erder-Stone theorem or Turán's theorem or Mantel's theorem, right? Remember, in like Turán's theorem, the examples we were looking at were just like, take your vertices, break them into sets, and put all the edges across. Like, that was a very simple example. But the examples in these theorems, for the bipartite case, they tend to have a kind of algebraic or geometric structure. And so that makes it very kind of difficult to find these examples. Determining the order of magnitude of these extremal numbers for bipartite graphs is a very difficult problem. We're going to see a bit more of that tomorrow when we're going to talk about cycles. So what is the extremal number of an even cycle? So if it's a 4 cycle, that kind of connects to what we did today, because a 4 cycle is just a K22, okay? But what about a 6 cycle, an 8 cycle, and so on and so forth? So what's the extremal number of those things? And like a kind of spoiler alert is the answer is, again, we don't know. We have upper and lower bounds, but we don't actually know the extremal number of an even cycle, except for some very small isolated cases, just like in the complete bipartite graph case.